If anybody feels like grabbing the camera and working the Zoom, feel free to. Otherwise, we'll just have to have a picture of me talking on there. So we tried to cover a little bit on Tuesday and the week before that to introduce you to the different ways that that molecules store energy, the molecular systems store energy. And we saw a bunch of different ways, including translational energy and potential energy. And those are the two big subgroups. You got translational kinetic energy from rotation, vibration, translation, and then you got potential energies that are stored as a function of some kind of external field. So you've got either electric fields between molecules, or an external electric field, or maybe you have a gravitational field, or something like that. But essentially, your molecules can store energy in the form of kinetic and potential. And we looked at a bunch of different those different mechanisms. And so we're going to start talking about something that relates absolutely directly to those energy storage mechanisms, and that topic is heat capacity. And the heat capacity is defined mathematically as the amount of heat needed to be inserted into a substance in order to raise its temperature by a given amount. And what's that? There's a textbook, one of the ones that I'm working from, that kind of laments that the thing is referred to as heat capacity, because it's not necessarily these energy changes don't necessarily have to be brought about by heat. You can do work on something, and then the work can later on be the energy delivered as work can be disseminated through the body. And at the end of the day, whether you did heat or whether you heated something or did work on it, the changes in energy are the same regardless. But what the heat capacity again does is it tells you how much energy you're going to need to stick into a body in order to raise its temperature by a certain amount. And before we get on with this subject, I want to kind of introduce a little twist on the subject of temperature. I want you to think of temperature, the temperature of a substance, as in a slightly different way. We looked at ideal gases, and we saw that the temperature of the substance was a measure of the average kinetic energy in the gas for the ideal gases. So loosely, temperature is related to the total energy of a system. We know that heat flows from one system to another if there is a temperature difference. So if one system is a higher temperature than another system, and there's a mechanism through which they can exchange energy, either through direct contact or through those action and distance forces. If there is a mechanism for energy transfer, energy is always going to flow from a body of higher temperature to a body of lower temperature. And so an analogy that I like to use for temperature is it's a measure of how much thermal energy is available in the environment around you. So the hotter the environment is around you, the more energy that is out there and that you're able to take in if you have a temperature difference between you and the environment. And so I like to think of temperature as a big bath of water. And I like to think of the heat capacity as being spaces within inside a porous rock or something that you immerse in that water. And so you have, I should use two different markers. You take a rock that has pores in it and dip it in a bath of water. And wherever there are pores that are below the level of the water, the rock is going to take on water, and it's going to fill it, right? And so, remember, this is just an analogy. And so, if our outside bath is at this height, we'll be able to store however much volume of water we can fit into those holes, right? And if we raise the volume of the bath up to a new point, we can fill in whatever holes are below that level. Temperature, the temperature of the surrounding area is analogous to this, can be used as an analogy to this water, in that when you have a hot material or a hot surroundings, you're able to pull in energy from that surroundings, but there are conditions under which there are conditions under which the energy transfer has to obey, and essentially that is that any change in energy, any population of a state has to be approximately on the order of the difference between two states. If you're going to, take a system and raise it from one state to another, like say you're exciting a vibrational state or a rotational state, the difference in energy between the two states has to be approximately on the order of Boltzmann constant times the temperature. And so as your temperature increases, this factor, Boltzmann constant times the temperature, increases. And what that's telling you is that at higher temperatures, you have higher energy states that you're able to fill. If the gap between two states is very large, you won't be able to populate that state at a lower temperature. But if the temperature raises to the point where the gap is on the order of kBT, then you're going to be able to pull in that energy from the environment to populate your state. So the same way that we had to have a higher water level in order to populate higher energy states, we had to have a higher water level to fill higher level holes in our porous rock. We have to have a higher temperature in order to populate higher energy level states. So every molecule has all kinds of different ways that they can populate or that they can hold energy, but some of the distances between those energy levels are larger than others, and larger energy gaps are going to require a larger ambient temperature before we can take in energy from our environment and store them in our molecules. Did I make the analogy clearly? Okay. And so what we're going to do, we're going to give a quick reminder of the different ways that the energy can be stored. We've got phase changes. We saw how a phase change can result in a difference between two energy states, or phase change requires a jump in energy. We saw that chemical reactions are a way to store energy. If you go from a low bond potential to a high bond potential and reactants goes to products, then you're storing energy. We saw how motions of electrons were able to store energy because of the potential energy between the electrons. This also leads to radiation. And we looked at translation, rotation, and vibration of molecules. You can read that page. It's just basically the same discussion we had last time. The kinetic energies are stored in translation, rotation, and vibration. I put a little comment in there that notes that some vibrational rotational modes are able to be populated by absorption of photons. So that's just, it's not a big deal, but I just thought you might want to know that and go into it later if you like. I want to go through a couple of examples of the way the specific substance will begin to store energy as you increase its temperature. We're going to take a substance. This is the system we're going to use is chlorine gas. So chlorine, pardon me, not gas necessarily. Chlorine can exist in the solid, the liquid, and the gas states. When it's in the solid state, it has a certain heat capacity. That heat capacity changes as it moves from the solid to the liquid, and it has a different kind of heat capacity in the liquid state. And when you move from the liquid to the gas, its heat capacity changes yet again. And there are reasons for this. In the solid state, materials can take on energy in two principal ways. First of all, Vibration of individual molecules, it doesn't necessarily apply so much in the solid state. In the solid state, the whole bulk of the matter vibrates. So you heat a piece of metal and you're starting to create vibrations between the metal atoms, or you heat a piece of any solid and you're going, or a molecular solid, and you're going to start creating vibrations between the molecules in the molecular solid. The molecules themselves don't necessarily take on the discrete vibrational modes that they take when they're not in the solid phase, but it's their vibrational modes that the whole bulk of the solid takes on. And this is one of the ways that the solid can hold energy, is by vibrating. There are two other ways that energy can get poured into a solid or expended in a solid as you heat it. And these are two important ways. One of the first ways is that materials that have intermolecular forces experience attractions, or generally they're intermolecular attractions. Materials that experience intermolecular attractions, if you want to expand their volume, if you want them to grow in size, you're necessarily going to have to create increased spaces between the molecules or atoms in the material. So the distance, the average separation distance between these molecules or atoms has to increase if the volume of the solid is going to grow while you're heating it. And we know that many materials grow or expand when they're heated. And so if there are these strong intermolecular forces, you're going to have to compensate for those forces in order to drive the molecules aside from each other, apart from each other. So what kind of energy storage mechanism is that? If we're separating these molecules from their intermolecular attractions, in what form are we storing energy that we put into them? Let's draw a picture of it real quick here. So maybe it's water. Maybe it's solid water. That's an easy one to draw. Right? We've got these HOHs, and they're all attracted to each other by their dipoles, right? And we want to increase the volume of this solid. And when we do that, the separation distance between the molecules is going to grow. Right? Now, wasn't there an attractive force between these atoms? And so when we acted to separate these guys against their attractive forces, we stored energy into what kind of a field? The electric field, right? Each of these molecules, they could be molecules, they could be atoms, are exerting attractive forces on each other via their electric fields. And so if we want to separate them, increase the separation distance, we're going to have to fight against those electric fields. And when we do so, when we separate something against the electric forces, we turn one form of energy into another kind. What kind of energy do we ultimately end up with? Potential energy, electric potential energy. Same ways we have that gravitational potential, right? You separate these guys from their forces, you're now at a high potential. If you were to, subsequently release them and allow them to attract to each other, they would move back down to a low potential. And so, for systems that feel intermolecular forces, they're bound together by intermolecular forces, if we affect a volume change on the system, say by heating or something like that, we're going to have to overcome those forces. So far, two ways. We're heating a solid, we can increase its vibrations. If we grow its volume, so vibrations, translational kinetic energy, if we grow its volume, we're storing energy inside of an electromagnetic potential between the molecules in the substance. And there's one other way that an expanding system, uses energy, It doesn't necessarily store the energy there in this manner, but it does use the energy. And that is that there is always an energetic debt that has to be paid if a system is expanding against an external pressure. So we'll draw this out. The mechanism that you're, the tool that you're used to be taught, or that is used to teach this expansion work, is a piston in a gas in a chamber with a piston on top. So I'm going to draw that. So in this setup, we can actually use a mass sitting on top of a piston to substitute an external pressure due to atmospheric pressure. Generally, when we're expanding against pressure, it's due to the atmospheric pressure, right? You've got a beaker full of water and you heat it. The water grows in its volume and it expands against the pressure of the gases in the atmosphere that are beating down on it. Well, we can simulate that by simply saying we've got a mass sitting on top of a piston, and that's providing the external forces. So if this gas is to expand, it's going to have to push back those forces that are acting down on it from the external environment, right? Now, that external pressure is a force over area. With a force over area. In the case of the mass, the force is mgh, mass times gravity times height over area. Total force then is going to be pressure times the area. Right? So if the pressure is force over area, then your total force is going to be pressure times the area. So if you have a total pressure P external on this thing, and you want to calculate or turn it into a total force, it's going to be that pressure times the area. And the work or energy expended is equal to the force times the distance. And so we can write this as the total work done in expansion is equal to the total force times the distance. So it's the pressure times the area, and the distance traveled is just whatever that distance is that the piston moves in the vertical direction. We can call it h if you want. But you'll notice that we've got the height of this piston travel multiplied by the area of the piston. Well, that's just the volume, the total volume change of the system when the piston when the gas expands and pushes the piston. And so our new equation for that expresses the energy spent in expansion is that our work is equal to P delta V, right? Area times height, that's the change in the volume. We've got that pressure external times the change in the volume. We want to write this out in a way such that a positive change in volume will require an expenditure of energy, right? Because if our volume is growing, we're spending energy. And so we'll put a negative P external right there and say that our work is P external delta V, and that gives us a differential form that we can write that says the differential form of work is negative P external dV. This is expansion work. So anytime a system is expanding and growing in its volume, if there is in fact an external pressure, it's going to have to spend energy to expand against that pressure. If you expand against a vacuum, you don't necessarily spend any energy because there's no external pressure to push against. That's what's referred to as a free expansion. Expansion work is important. So we're looking at the solid phase. So there's two places where we have to pay in order to expand. We've got to pay to separate molecules away from their intermolecular attractions, and we have to pay to expand the system against the external pressure of the environment, right? So for solids, we've got that kinetic energy associated with vibration, or movement of electrons when the solid heats up, if it's going to move like a black body. We've got work against internal forces that we have to do if we're going to expand while heating, and we've got that work against the external forces that we have to do as well. From the solid phase, the next step that we get to is the solid to liquid transition. Solid to liquid transition is another example of separating things against their intermolecular forces. In the solid phase, you got strong intermolecular forces. If you're going to want to break them apart, you're going to have to stick energy in, and so there's energy consumed in moving from the solid to liquid. Also, if there were a volume change in moving from solid to liquid, you'd have to pay for that volume change as well, due to any external forces and from an external pressure. So, solid to liquid transition has some of the same energy components as, it stores energy in the same ways that the solid phase does with heat. Once you get to the liquid phase, one of the things that happens is that you retain in a liquid all of the different vibrational modes that a solid has, but you gain a few extras. Now in the liquid, the individual molecules, their individual vibrational modes become relevant. A lot of vibrational spectroscopy is done in the liquid phase. And so you gain vibrational modes. There are also other translational kinetic energy modes. In the liquid, the bulk of the liquid can move around and currents can develop. And so there can be translational kinetic energy stored in currents within the liquid. And then again, within the liquid, if the liquid's expanding, you've got those same two payments that we spoke of earlier. Energy to expand against internal forces and then energy needed to expand against external forces. It turns out that in general, the liquid phase has more different modes of energy storage than does the solid phase. And so the way that you can envision that with our analogy with the rock is that when you say this is the liquid to solid transition line, solid goes to liquid. When we cross that boundary and we move from the solid into the liquid, there becomes a higher density of pores in our rock. There's more different ways that our rock can hold water. There's more different ways that our molecular system can hold energy when it's in the liquid phase than when it's in the solid phase. Your liquid to gas transition. Again, if there's a volume change and liquid goes to gas, there's definitely going to be a volume change. You're going to have to put energy in to overcome intermolecular forces. You're going to have to put energy in to overcome external forces. And in the gas phase, you lose a lot of those vibrational modes that you had previously. We said that the liquid phase and the solid phase both had vibrational modes, and those modes end up storing a lot of kinetic energy. In the gas phase, those modes disappear, you don't have them, and so as you transition from liquid to gas, the number of different holes that our rock has, the number of different ways that we have for storing energy decreases. And so the heat capacity actually drops when you move into the gas phase. One thing that does happen in the gas phase that wasn't present in the liquid phase is that you end up being able to get rotational modes excited in molecules. It's hard to excite rotations in the condensed phases and the liquid and solid phases because there's too much friction between adjacent molecules to get them really to begin rotating. So these are all mechanisms of the utilization of energy by a system. Only some of these mechanisms actually technically result in an increase in the internal energy of the system. And specifically, the work that we do in expansion is not defined as a potential energy. It's energy that our system has given away to the surroundings. So if we have an external pressure pushing on us and we want to expand against it, we don't necessarily store a potential energy by expanding against that pressure that can then be restored later. We say that that's energy that's given away. However, if we expand against an internal pressure, against those internal forces, in that case we do consider the energy to still be contained within the system because it's energy that's acting between the molecules in the system. So you need to know that certain types of energy spent in expansion stay with the system, and other types of energy spent in expansion leave the system. I'm going to play with that here. Moment or 4. So this is what it looks, what the heat capacities look like for CL2. It's just a rough sketch. Heat capacity starts off very low in the solid phase, and then as the temperature grows, as kVT grows, and we're able to have enough thermal energy in the environment to populate our excited states, the heat capacity increases with temperature. We saw that the liquid has a higher heat capacity than the solid, and so when we get to that solid-liquid boundary, the heat capacity increases. And then we saw that the gas had a lower heat capacity than the liquid, and so when we cross that liquid to gas boundary, the heat capacity drops. Now this isn't to suggest that we drop in energy when we go from liquid to gas. We know very well that when we move from liquid to gas, we're going to higher energy. The question isn't how much total energy is the system holding. The question is how much energy is it from that point forward? How much energy can it store in whatever modes it has? So from whatever state it's in, where are the different storage mechanisms, or what are the different storage mechanisms that are available at that state? And so when we go to the gas state, the number of storage mechanisms decreases. We're still at a higher energy level. We just, the next piece of energy that gets put on top of us, we have fewer places to put it. Incidentally, I told you that we can't put energy into a state unless the difference between two states is on the order of kVT. And there's a little estimation of the, or approximation of the different energies required to populate translational, rotational, vibrational, electronic states, you see that the translational states are really low in energy. They're on the order of 10 to the negative 41 joules. And so translational states in matter begin being populated right away. Rotational states, if they're available, are on the order of 10 to the negative 23 joules.